Good morning, and welcome to today's electronic design webcast. Our topic today, Enable Smarter Automotive Sensor Integration with Millimeter Wave Antenna on Package Technology, is sponsored by Texas Instruments. I'm James Mora, a senior editor with Endeavor's Design and Engineering Group. To start, let me explain how you can participate in today's presentation. First off, if you have any technical difficulties during today's session, just type in your issue into the Ask a Question box, and a member of our team will assist you. We also welcome your questions during today's event. We will answer as many as possible during the Q&A session following the main presentation, but please feel free to send in your questions at any time. To do so, simply type your questions into the Ask a Question box and click Send. Also, please be aware that today's session is being recorded and will be available on Electronic Design's website within the next week. You'll be notified by email when the archive is available. Now let's meet today's speakers. After working with TI's automotive and industrial radar teams, Mark Sand's current focus is in the automotive in-cabin radar market, specializing in gesturing technology. Sarah Dominy joined TI in 2015 as a failure analysis engineer, performing root cause analysis for customer and qualification failures. Her current focus is now automotive near-field sensing radar. Now let me turn things over to our presenters. The floor is yours.
Hello, everyone, and thank you for joining. My name is Sarah Dominy, and I'll be joined by my co-presenter, Mark Sand. We're excited to present TI's new Antenna on Package, AOP, millimeter wave radar sensors for automotive applications. So what is millimeter wave radar? Millimeter wave radar is an RF technology, and it is the most reliable and robust sensor on the market. Furthermore, it's intelligent, giving you more data with high accuracy, such as an object's distance, its range from the sensor, how fast the object is moving, its velocity, and the direction the object is moving, so its angle. Where other sensors like LiDAR and ultrasonic fall short, radar continues to reliably work in challenging weather conditions, such as darkness or bright light, rain, snow, mud, etc. TI's millimeter wave radar will take your sensing needs further with our new Antenna on Package, AOP, technology. It's a single chip, low power, RF CMOS technology solution. We offer radar sensors for both automotive and industrial applications. For today's session, we will be focusing on automotive applications only. So next, let's talk about the RF CMOS technology evolution at TI. When TI started developing RF sensors, as shown on the left, we provided a two-chip solution, one PCB for the transceiver and one for the processing. And as TI innovated, moving to the right, we produced a single chip solution. This eliminated the complex routing of two PCBs and reduced the noise, resulting in a much smaller chip with a simpler design and with higher resolution and accuracy, as well as low power. Now, TI has innovated even further, presenting on the far right the Antenna on Package, AOP. It has all the advantages of the single chip device. Plus, the antenna is on the package, making it the smallest offering to kickstart your development. So now let's dive deeper into what AOP is. So generally, in a traditional RF design, there is an external antenna, as shown on the left, and it's in the silver area. This requires extra routing on the PCB and expensive material like Rogers. So for AOP, we eliminate the entire silver area, and it makes it 82% smaller, as shown in the middle. AOP also allows you to design an only RF4 material, making manufacturing simpler. So with TI's AOP, we will save you the time to market for not needing to take into account the RF design. We've taken care of that. And because we've eliminated the board routing and all of that space and the expensive material, the cost is reduced. But we're also increasing the performance, since now we'll have better gain, higher efficiency, less losses, and less noise. And it's going to be highly accurate with less than 4 centimeters range resolution. So now let's discuss the AOP portfolio at TI. We are offering 2 devices in the 4 gigahertz wide bandwidth. A 60 gigahertz from 60 to 64 gigahertz AWR 6843 AOP device as shown on the left for in-cabin applications. We're also offering a 77 gigahertz near-field sensing for the body in the 76 to 81 gigahertz range, AWR 1843 AOP, as shown on the right. We're offering in these 2 frequency bandwidths to comply with regulations that most countries are following for the automotive radar. Also, the TI advantage is that if you purchase multiple TI devices, they are pin-to-pin compatible and use the same software. So this is a saving in your investment and your learning time. Now, for our AOP portfolio, we have provided a solution to the following applications. For in-cabin, in the 60 gigahertz bandwidth range, we have provided a solution for child presence detection applications, vital sign monitoring, occupant monitoring, gesture detection. And for near-field sensing, we have provided an AOP solution for door obstacle detection, trunk obstacle detection, and ultra-short range radar, including parking and entry-level blind spot detection. We'll delve further into the following applications in the next few slides. So now I'd like to talk about the antenna on package applications for near-field sensing, including the trunk and door obstacle detection I had just mentioned, as well as the parking and entry-level blind spot detection, BSD. So first I'll talk about door and trunk obstacle detection using TI millimeter wave radar. So before, what's likely to happen in everyday life is you park closely to someone and they accidentally hit your car when opening their door, or you hit someone else's car and it's this costly thing. It's annoying, you always have to look at it, it's unsightly. And I know I personally want to avoid damage on my own car. And we now have the technology to avoid that. And it looks seamless in the automotive vehicle. You won't see the appearance of it. So before we had damage, as shown in the left, it's very common and easy to occur in everyday life. And now we have a safe door opening option. So you can avoid that collision and that eyesore. We also provide a safe trunk opening. So again, you'll avoid that eyesore on your automotive vehicle. Now, when talking about the door and trunk obstacle detection, there is another ultrasonic on the market. So with ultrasonic on the market, you'll see that it's going to be much less accurate than radar. And you're going to have to put these unsightly holes in the body of the vehicle. These unsightly holes also will render unfunctional when covered with mud or snow or other things. Pollen is really bad in Texas, for example. So then it's not even going to work. It's not going to work consistently like we know our customers want. It's also going to lack the 360-degree coverage that can be easily accomplished with radar. Now, with radar technology, you can see on the right that it's with the AOP Advantage, it's so small it can fit in your door handle. It looks beautiful on the body of the car because you can't see it. There's no obstruction to the design of the vehicle. And furthermore, it's going to be that highly accurate solution that we've discussed with a wider field of view with azimuth, AZ, and elevation, EL, of 140 degrees. With just a few sensors, you can accomplish that 360-degree coverage that ultrasonic cannot and would require much more sensors for ultrasonic than what radar can do with just a few sensors. And it's going to be that robust detection so it always works. We want something that always works as a consumer. Next, I'll talk about the applications of parking and entry-level blind spot detection. So the same sensor can be utilized for other applications such as this. So if you are using it for the door and trunk, it could be also utilized for the parking and entry-level blind spot detection. So it can help you park as shown in the left image. And when using it in this parking mode, the range can be extended to up to 50 meters. It's going to have that same wide field of view of the azimuth and elevation of 140 degrees. And it's going to still have that robust detection. So it can detect objects at different velocities and different material types, such as cart, plywood, pipe, plastic cones, as shown on the right. So thank you for listening, and now I will pass it over to my co-presenter, Mark.
Thank you, Sarah. Hi, everyone. So I'm going to be discussing and diving more into the AOP applications for in-cabin auto space. I'll be looking at the umbrella of occupant detection and the applications that covers, as well as focusing on gesture sensing. So currently, a lot of auto solutions for this space include using ultrasonic sensors or weight sensors, even some camera-based solutions. Some of the fallbacks here, although they do work in most scenarios, is that there are potentially false positives. And given a specific use case of a child potentially being left in the car, say a newborn baby covered by blankets, rear-facing in the back seat, a camera may not be able to necessarily sense their presence or sense their heart rate. With millimeter wave radar sensors, we're able to detect occupant presence, as well as position for seatbelt reminders, airbag deployment control applications, as well as even detecting a child left behind, as it can potentially sense their materials and sense heart rate with vital sign monitoring. Another benefit here is that because of the small form factor and the wide field of view, it's able to be placed in multiple locations in the vehicle and very flexible. As you can see from these two solutions that we have, demos listed on our TI Resource Explorer, that's our sort of demo library that we have available. We have a front mount occupant detection demo, as well as a roof mount occupant detection demo, showcasing the variability of potential placement, as well as the range and the range resolution, as you can see being 5 meters to 7 meters and a 4 centimeter range resolution, therefore covering the entirety of the in-cabin space, as well as the accuracy and the resolution within that. Another thing to note is that because our solution uses a point cloud based data collection, it doesn't actually encroach on the privacy of the individuals. Camera-based solutions that exist today can potentially showcase people's faces, and with our point cloud data solution, this is not something to worry about. Another thing to note is that our devices are multimodal, meaning that they can function using multiple applications based on the state of the vehicle, meaning that potentially the vehicle could be turned off and you could be detecting your child as the device is in a low power mode, versus when the vehicle is running, you could also be functioning as a different application, in this case potentially using gesture sensing, which I'll be going into detail here. So a lot of current solutions for gesture sensing, or if they even have gesture sensing, I mean, you have knobs and dials that you can turn to adjust potentially HMI control, light control, media control. But with gesture sensing, you wouldn't have to necessarily avert your eyes from the road to look down at a button or a knob to turn. You could simply wave your hand. We have a demo available, multiple gesture and motion detection, again on TI Resource Explorer. And a lot of the benefits here include that you can potentially place this in different parts of the vehicle, most likely in the central dashboard infotainment control module. It's very accurate. It can detect, again, with a 4 cm range resolution, and it has a wide field of view of 120 by 120 degrees. We have shown here one of our EVM, that's evaluation modules, so you have the ability to test this on your own and evaluate with the software we have available. Another pro, like I was saying before, is that you could potentially just use this with the multimodal functionality, so you could use one sensor for multiple applications. Moving on, again, looking at application scalability, here are some use cases, again, that we could use for multimodal functions. You could potentially have the sensor detecting intruders, which is something that may not be possible with other sensors, as the car could be powered off. It could be functioning on a low power mode. And you could have the same sensor being used for multi-row occupant detection for various functionality, as it's able to identify and detect each of these individuals. And concluding here, I think one of the biggest pros that TI has to offer is that we are with you every step of the way. Throughout the whole product lifecycle, we have the resources available for you to evaluate with our evaluation modules, as well as TI designs and software for you to test. We have the silicon available for you to purchase to integrate into your devices and end consumer products. We also have the ecosystem partners available, third parties if you need, to connect and help you through that design process as well. And when you're going through and debugging, we have the support available through our TI E2E, that's engineering to engineering community, which is a forum set up for you to ask those questions. And we have training videos and other collateral available for you to have access to and get those resources that you need. And finally, wanted to conclude this presentation with some resources available for you. On the left, we have the in-cabin resources. We have a TI design for that child presence and occupant detection demo that I was mentioning, as well as a technical article. We also have the evaluation module for the 6843 AOP device mentioned before, if you want to test out that software and evaluate different use cases on your own devices and own situations. We have occupant detection as well as driver vital sign monitoring available. And we also have that silicon available in data sheets at your leisure. On the right, we also have the 77 gigahertz space for near field sensing. We have a TI design for obstacle detection, as well as the AOP EVM for 1843, which again is the 77 gigahertz space, obstacle detection videos, as well as ultra short range radar demos, and the silicon available for you. Wanted to conclude by saying thank you all for listening, and we're now going to open up the floor for any live Q&A that you might have.
All right, a few of you have already submitted questions, so we're going to jump right in. If you'd like to submit a question now, type your question into the question box and hit the submit button, the send button, I'm sorry. The first question we have here is, where would the typical sensor placement location or locations be within and outside the vehicle?
Hi, great question. I'll take that one. So it depends on which application you're trying to achieve. But for instance, if you're using the sensor for a door obstacle detection application, with our reduced form factor, that really small size, it can fit in a place like the door handle. And if it was for that trunk obstacle detection, it could fit in the trunk handle or the back bumper without needing the holes. And if you are using it for the application such as gesture detection or occupancy, it would be in the dashboard or the headliner, for example. Thank you.
All right, so the next question goes, what is the on-chip antenna direction diagram relative to the package in PCB?
Sarah, do you want to take that?
Hi, sure. Could you expand on that question, please?
While we wait for maybe that audience member to expand on their question, we will ask another one. So we have another question here that goes, what radar waveform approach is being used at TI?
That's a great question. I can take that. This is Mark. So at TI, we use a frequency modulated continuous wave radar approach. That's FMCW.
All right, so we have another question. It is, what other millimeter wave radar devices do you have in your portfolio besides the AOP shown here?
Hi, I can also take that. 1 second. So within our portfolio, we also have other devices besides the AOP. As you can see on the screen, from left to right, we sort of have different levels of integration. We also divide by 60 gigahertz versus 77 gigahertz for in-cabin versus near-field. Essentially, the AOP device that we've been promoting here is the most integrated solution that we have. As you can see with the system diagram here, we have the DSP, more memory on the chip, as well as obviously the antenna on package. So it's, I think, the most easy to use in terms of your design process. But if you want more of a front-end type device or just sort of a lower power device, we have for the 77 gigahertz, the 2243 on the far left, and then moving towards the right, you have higher levels of integration if you want more functionality or capabilities depending on your use case and application. And then for 60 gigahertz, we have the 6443 as well as the 6843 listed above. And again, it's just sort of the different levels of integration based on your use case.
All right, so we have another question here that is, can the same sensor be used for child presence detection and gesture control, meaning only one sensor in the headliner?
Yes. So because our sensors have multimodal capabilities, you could essentially use it for child presence detection. When the vehicle is turned off, the sensor would be in that low power state. So it could be sensing that child within the vehicle versus when the car is powered on, the device would be in a different state and then be functioning as a gesture detection type sensor.
So the next question we have is there any way to reach 360-degree coverage around the body of the vehicle?
Hi, sure, I'll take that one. Yes, you can reach 360-degree coverage. It would take about 3 to 4 devices of our sensors to achieve that around the body of the vehicle.
Okay, the next question, can I get access to the ADC's raw data?
I'll also take that. Yes, you'll be able to get access to the ADC's raw data. We have a great white paper on TI.com that goes into this into more depth. But essentially, yes, you'd be able to look at the raw data and by utilizing our software and interpret it. And the white paper application paper is the millimeter wave radar device ADC raw data capture. And it would be linked under the technical documents for the AOP devices.
Okay, the next question is, can I use one sensor for multiple applications?
Yes, so I kind of answered that earlier with another question, but essentially, yes, with the multimodal capabilities, the car could be powered on or off, and based on the state of the vehicle, the sensor could have different applications that you program such as the child presence detection when it's powered off, or potentially when it's powered on, gesture presence or occupant detection.
Okay, so another question asks about what is the minimum operating distance?
So based on the form factor and just overall technology of the device, the minimum operating distance is 4 centimeters based on range resolution as well.
All right, and we have another question here. What determines the radar's maximum range and what are the ranges?
Sure, I can take that. The maximum range is a factor of many elements, such as the number of PX transmissions together, like the transmit power, the type of antenna, the processing chain, and the type of object. And for these sensors, they're developed for near field around the body or in the cabin, but for the body, the max range would be the 50 plus meters. Thank you.
All right, we do have a little more time, so maybe we'll wait a few moments to see if any additional questions that we are going to ask live will come in. So. All right, well, that seems to be the last of the questions that we are going to be answering live on this webinar. And so for those questions that maybe are coming in as we wrap up the call, we will get back to you via email. And so that concludes today's presentation. On behalf of Electronic Design, I'd like to thank Texas Instruments for sponsoring today's event, and of course, all of you for joining. Have a great rest of the day.